Teacher, if you are speaking, we are not hearing you.
Okay, so let's go on. So last time we have introduced the Newton's laws, the first law and second law and third law. So the first law tells that if there's no force on this object, it will keep on moving with in a straight line with its velocity or at rest. So, but if there is a force, so we need to use the second law. So we need to define the mass. Mass. So the mass is the measure of energy of a body. And according to Newton's second law, so the force for F should be equal to ma, the mass, and acceleration. And we can also use differential form dv over dt. And according to the third law, whenever one object exerts a force on a second object exerts an equal and opposite force on the first. So, and we have introduced the different kind of forces like the gravitational force and gravity. Okay, so I will mark you later. So the elastic force is caused by the change in shape of a solid. And actually, in fundamental physics, we have only 4 types of forces. The elastic force and friction, actually, they are special kind of electromagnetic interactions. And the first two can appear in any direction, but the strong interaction and the weak interactions, they appear only inside the nucleus, which means the subatomic level. So to solve a problem, usually we use the following procedures. Like the first one, you should draw a diagram to show all the forces on each object. So separately, and then resolve the forces into components. And on each direction, we use the Newton's second law to build the equations, and then we solve the equations. We can solve the problem. So previously we investigated the apparent weight on a scale. So the scale actually it does not really tell you the weight. Actually, it tells you the normal force that the person exerts on the scale. According to the Newton's third law, it should be equal to the normal force that the scale exerts on this person. Usually it's not equal to the weight unless you are on the ground who has no acceleration. So if you are moving downward with acceleration g, the read of the scale should be 0. That is called loose weight. So this is about a scale. Okay, so let's go on to this one. So let's investigate another example. This is called Atwood's machine, which is the basic model of the elevator. So a system of two objects suspended over a pulley by a flexible cable is sometimes referred as an Atwood's machine. So just like a elevator, we have a elevator car and a counterweight. So the mass of the elevator is ME and the mass of the counterweight is MC. So we can, this is a basic model for the elevator, and we leave the motor out of the system of this calculation, not consider the simplest case. We can also ignore the mass of this pulley. Remember that if we consider the mass of pulley, the result could be completely different, and we will introduce this situation in the next chapter. So here in this chapter, we do not consider the mass of the pulley. We do not consider the motor system. We just consider system formed by this elevator and this counterweight. So, okay. So, mass of the empty elevator is 850, while when carrying 4 passengers, it can be 1,150. We need to build a model, a simple model. Just like here, an elevator, we can treat it as a point, a mass point, a particle, and the content will also the counterweight as a particle, 2 particles. And we have ignored the mass, so we don't need to consider this part. So only 2 objects, this one and this one. And we need to analyze or find out the forces on these 2 objects. So let's see here. So for the elevator, we can also ignore the drag of the L. So for the elevator, the gravity, mg, M-E-G, is the gravity of the elevator. And the tension because of the cable. So the tension because of the cable in this direction should be, let's say, T. And for the counterweight, also the mass, the gravity because of the mass, mcg, and the force due to the cable, also T, because if you ignore the mass of the pulley, the tension in the whole cable should be the same. Okay, and then we can choose a positive direction like this, like we choose it to be Y or X, that's the same. So 2 objects, on each object, 2 forces. Okay, so and we can draw this picture. This is called free body diagram. In this diagram, you need to tell the others the forces and the positive direction. So just like here. The force is on the so on this one, and the force is on this one, and okay, so we can then with second step we can choose one direction to be positive, like this direction to be positive, and we can then try to apply the Newton's second law for each object and on y direction. In y direction, so in y direction, so that's for this object. That is ft is in positive direction, so that's positive, and m1g is in negative direction, so it's negative. That the net force is ft minus m1g. Here m1 is the mass of the m1 is the mass of the, let's say, the elevator, right? So should be equal to, if the acceleration of this is upward, is moving up, so that is ma1. m1a1 is positive because it's in positive direction. So, and for this counterweight, so the also ft minus m2g. m2 is the mass of the counterweight, which is also mc. So it should be equal to, like, okay, a2 is downward because they one move up and the other must be moving down, right? They cannot both moving up. So this one moving up, this one moving down. So a2 is in the negative direction. That's why here is minus m2a2. Okay, there are two equations. We want to solve a_t and a1, a2. And there are three variables, but only two equations. It's not enough. So we need to find out the relation between a1 and a2. There is a very important, there's something important here. So that's the length of the cable cannot be changed. It's a fixed length, right? The length of cable should be fixed. So if this one is moving up with some velocity v, and this one must be moving down with the same velocity v. If this one is moving faster, this will break this cable, right? Because the length of the cable cannot change. It's fixed. So that means the speed of this one should be equal to the speed of this one at any time, which also means the acceleration should have the same magnitude. They should be equal to the other. That's why a1 should be equal to a2. If they do not have the same acceleration, after a few seconds, the speed should be different, because originally they start with the same speed. So if the speed is different, that is not possible, because the length of the cable is the same, and they are connected with the cable. So you cannot change the length of the cable. So that's why there's one more equation, a1 should be equal to a2. So now we have three equations, and we have to solve three variables, this one, this one, this one. So that is possible. So, okay. So a1 and a2, they have the same magnitude, but in opposite direction. So we can solve the acceleration and also the tension. So that's how we solve problems. We first step, we draw a diagram and show all the forces on each object. And then we apply Newton's second law on each object in x and y direction. And then we solve the equation. Sometimes we need to find the connections between these two objects. Okay, so that's so let's look at this example. This is a model of something called accelerometer, which can be used to measure the acceleration. It's a simplest accelerometer. So a small mass, m, hangs from a thin string, and it can swing like a pendulum. You can attach it above the window of your car. When the car is at rest, the string hangs vertically. What angle does the string make when this car accelerates at constant acceleration? A is equal to 1.20 meters per second square. And when the car moves at constant velocity, V is equal to 90 kilometers per hour. So, if we ignore the resistance of the L, when the car is moving at a constant acceleration, A is equal to 1.20 meters per second square. According to the law about inertia, this ball hanging with this string should moving with the same acceleration because it's connected to the car. They move together, right? They move together. So this ball will also moving with a acceleration, this acceleration. So, but if it does not change its direction, it's still hanging vertically, it's not possible. Because if it's hanging vertically, the force on it all in vertical direction. The tension and the gravity, they are all in vertical direction. They cannot produce a acceleration in horizontal direction, right? So in order to produce an acceleration in the horizontal direction, we need a force, at least a complement of that force along horizontal direction. So that's why there must be an angle relative to the vertical direction. Because if it's still in vertical direction, it's not possible. So in order to produce a force complement in horizontal direction, so let's see, okay, this is the ball. This is the mass, the gravity due to the mass, right? And if we need, because the car is moving to the, let's say to the left. So if to the left with acceleration A, so the ball also moves to the left. So that which means the net force, or at least the force in horizontal direction should be to the left. So in order to produce a force to the left, the tension must be in this direction. The tension should also be along the string. So that's the direction of the string. The string should be in this direction. so that it can produce a tension in this direction, and it has a component in horizontal direction to help us to produce this acceleration. So this is the vertical direction. If this angle is theta, so in vertical direction, the acceleration should be 0, which means if this is, let's say, ft, so this the vertical component. So if we use, here's y, here is x, so ftx and fty, ty. In y direction, it should be equal to, let's say, the vertical direction ft cosine theta. And it should be equal to mg, because in vertical direction it's a balance. But in horizontal direction, it's equal to ft sine theta, which is equal to, according to the second law, should be equal to ma. So if we know the mass, we know the acceleration, and we, in order to solve sine theta, we need to know the tension. So from this equation, this new equation, actually we can solve it, because with these two equations, so we know the acceleration. Okay, so that's the first step. Horizontal direction is ft sine theta is equal to ma, and in vertical direction, it's 0, because vertical direction, the acceleration is 0. So ft cosine theta, which is equal to mg. So we can cancel ft so that we can solve the angle. So when we cancel ft, so tangent theta should be equal to a over g. G is the acceleration near the surface of the Earth. So if we know a, we know g. So this angle is about 70 degrees. So by measuring the angle, we can actually measure the acceleration. So it has nothing to do with the mass of this ball, right? Because according to this equation, tangent theta is equal to a over g. So we know g, the acceleration near the surface of the Earth. So we can measure the acceleration a by measuring this angle theta. So this is the simplest accelerometer. We just hung a ball here, and when it is moving together with another object, we can measure this angle, and then we know the acceleration of this object. We know the acceleration of this, but we can measure the angle, and the acceleration should be equal to g times this tangent theta. Okay, this is the first step. But if it is, for the second question, when it is moving at constant velocity. So when it is moving at a constant velocity, which means the acceleration should be 0. Because the acceleration, according to the first law, if it is moving with constant velocity, the force is 0, right? The force is 0, the acceleration is 0. So and you can also understand another way, because the acceleration is the change rate of the velocity. The velocity does not change, which means the acceleration is 0. So if the acceleration is 0 according to this equation, If the acceleration A is 0, the angle is 0. The angle is 0. It will not change because this is, yes. Yes, what's your question? Which one? The y component, right? Okay. Why the y component is 0? Because it does not move in this direction. In y component is balanced. There's no acceleration. Y direction. Together they are moving in x direction, and the acceleration is a in x direction. Just like this car is moving in x direction, it doesn't move in y direction, and the ball is moving together with the car, right? Yeah, on the rocket, that's different. Yes, if the rocket is moving in y together, they are moving together in y direction. Yeah. That's for the rocket. So that's why we need to calculate. So in this case, there's only acceleration in x direction. But maybe in other cases, there can be acceleration in y direction. Okay, that's a good question. So this is a very simple device that can help us measure the acceleration. So as we mentioned, there's also another force which is called friction. Friction is everywhere. It's everywhere. So friction is the force caused by the roughness of the contact surface. So here, if we choose this part and put it under a microscope, you can see something like this. So that's why there's friction, because this zigzag part you can see the shape is like this. They tend to prevent the other one from moving, right? So but actually they can move because you want to change its shape, and maybe you overcome these tiny things and then pass through, but still you need a force. You overcome a force. That force is friction. So friction, if this force is very small, it will not move. It will not move, but it still there is friction. So this is called static friction. That's the friction between the surfaces when there is no relative motion. But when you increase this force or the force along x direction, it will start to move. To start moving. When it starts moving, the force becomes kinetic friction. And usually these two are, this kinetic friction is proportional to the normal force, but the static friction, it can change with the force you apply on it. So if we draw a diagram, this is the force component in horizontal direction. And originally, when you increase the force in horizontal direction, if the force is not in loss, this object will not move. And because in the horizontal direction, it's still in a balance, so that's why the friction will increase with the external force in horizontal direction. But when the force is greater than a critical value, it will move. It will move. It will no longer stay at rest. It will start moving. It will start moving. And and now the force becomes the kinetic friction. Usually the kinetic friction is slightly smaller than the maximum value of the static friction. The kinetic friction it usually is a constant. It's proportional to the normal force, but slightly smaller than the maximum value of the static friction. So that's why the diagram is like this. This one is smaller than this. And the friction, kinetic friction, if the speed is not very large, usually we can treat it as a constant. So that friction is caused by the roughness of the contact surface. Okay, so what exerts the force to move a car, or what makes a car go forward? So usually you will believe the force that makes the car go forward comes from the engine. But actually it is not. Actually it's not. The common answer may be the engine makes the car move forward, but it's not so simple. The engine makes the wheel go around, but it does not make the car go forward. Why? Because maybe you have this, you have this situation in the winter when you are driving on the ice. No matter how powerful your engine is, maybe you cannot move because it's so slippery, it's so smooth on the ice. There's no friction. So here, maybe it's a car. If the tires are on slick ice or deep mud, the just spin, it will not move. Actually, what makes the car go forward is the friction. So when it rotates, the force due to the tire on the ground is in this direction. But according to the Newton's third law, the force from the ground on the car is in opposite direction. So which means the force is in this direction. And the ground pushes the car moving forward, accelerate the car forward. And actually it's friction. Because according to the Newton's third law, if the force on the tire is friction, the force on the ground is friction, the force on the tire is also friction. So, but remember, there's something interesting for the car. That engine that's a two-wheel, maybe your engine only rotate these two wheels. The friction on this wheel will push the car forward, and but the friction on this wheel actually is in this direction. It will reduce this speed, But this one, obviously, this one is more powerful. So that's why you are still acceleration. But for the cars with four wheel, like the engine will spin both. The net force on this particle should be in this direction, point to the center, and it's the net force. So according to the Newton's second law, the force should be equal to ma. And this acceleration should be equal to v squared over r. V is the speed of this motion and direction towards the center. And according to the Newton's second law, the force should be equal to ma, which is equal to mv squared over r. R is the radius of this circular path. And also the direction is toward the center. So this is a uniform circular motion. That's the simplest case of circular motion. But sometimes it's not so simple. The speed can change. So then let's focus on the long uniform circular motion. So based on the uniform circular motion, there is acceleration in this direction, but the speed in tangential direction will not change. So That's uniform circular motion. So if the magnitude of the speed does not change, that means this force or this acceleration only change its direction, right? Because the magnitude does not change. This one is perpendicular to this one, so it can only change its direction. If we want to change its magnitude, we want to change the magnitude of the speed, we need a complement of acceleration along the direction of the speed, not perpendicular. Even it's perpendicular, it can only change the direction, it cannot change the magnitude. So if you want to change the magnitude, you need an acceleration or at least a complement along the direction of the velocity or the tangential direction. So that's why for non-uniform circular motion, there will be acceleration in both radial direction and tangential direction. The acceleration in radial direction is going to change the direction of the speed of the velocity, and the component in tangential direction is going to change the magnitude of the velocity. So the net acceleration depends on the sum of these two. So the acceleration should be the vector sum of radial acceleration and the tangential acceleration. And according to the equation on previous slides, the radial acceleration is going to change the direction of the velocity. So it's the same as that in uniform circular motion. It should be equal to v squared over r. But what's the difference? So, okay, let's take a rest. We will go on after 5 minutes and so we need to do it twice. So please. Okay. So the second time, so this one is different from third one. So okay, so I will wait a few minutes. So this one is different from the first time. Okay. Okay, so let's go on. Let's go on. the long uniform circular motion. So, the total acceleration should be equal to the vector sum of radial acceleration and tangential acceleration. The radial direction acceleration is going to change the velocity or change the direction of the velocity. And what's the difference from the this equation and the equation on previous slide for uniform circular motion? For uniform circular motion, the radial direction acceleration is the same, v squared over r. But for uniform circular motion, v is constant. But for long uniform circular motion, here in this equation, v is not constant. At different places, v can be different. But for uniform circular motion, v is the same because the speed does not change. So this acceleration is caused by the change in the direction of the velocity. While the tangential direction, it is caused by the change of magnitude of the velocity. So dv over dt means the change of the amplitude. Here v only means the magnitude of the speed of the velocity. It does not mean the vector. There's no arrow here, which means it's not a vector. It's the magnitude, the change of the magnitude of the velocity. So together is the total acceleration, and the direction of the acceleration is neither radial nor tangential. It depends on the other two, but neither of these two should be the direction of the total acceleration. So let's check this one. So if it is rotating like this, a small sphere of mass m is attached to the end of a cord of length r and set into motion in a vertical circle. Now it's a vertical circle, not a circle in the horizontal surface. It's in a vertical surface about a fixed point O. We want to determine the tension in the cord at any instant. At any instant, when the speed of sphere is v and the cord makes the angle theta with the vertical. So that means when it rotates to here, angle theta with the vertical, we need to calculate the tension now in this cord. So, okay, according to, so it's a circular motion. For circular motion, usually we do not use the XY coordinate. For circular motion, we usually solve the vectors into components along radial direction and tangential direction. Like here, the force on this ball is okay. The force on this ball should be the gravity mg, and tension T. This is what we are going to calculate. And we are going to resolve it into components along radial direction and tangential direction. So T, the tension, is already in radial direction, and we need to resolve this mg into tangential direction and radial direction. So if this angle is theta, this is also theta, because theta is the direction of the between the this direction and the vertical direction. So that's why here is also theta. So this component, mg cosine theta, and this mg sine theta. Okay, and this one mg sine theta, tangential direction. So we are going to calculate this because, and what we know is v, we know angle theta, we know this r, we know this mass. So along this direction, the radial direction, according to the equation, we know the radial acceleration AR should be equal to v square over r, right? The radial acceleration. And according to Newton's second law, the net force in the radial direction, the net force in radial direction should be equal to mass times AR. So the force in radial direction is T, like minus, because when the acceleration point to the center, right? So it's mg cosine theta should be equal to MAR, which is mv square over r. And we know the mass. We know g is the accelerated near the surface of the Earth. If we know m, we know theta, we know r, and we know v, we can solve the tension. We can solve the tension. T is equal to mg cosine theta plus mv squared over r. Okay. So T is equal to mg cosine theta plus mv squared over r. And we can also write it like this. We put mg together. And okay, let's check this. When theta is equal to, like we say, 0. When theta is equal to 0 at the bottom, right at the bottom, cosine theta is equal to 1. So T reaches maximum. So it has its maximum value at here, the bottom. At the bottom. Okay, but when it reaches the top here, reach the top, and at here, cosine theta is equal to -1, and here T, the tension and gravity are in the same direction, while here they are not in the same direction. They are not in the same direction. So that's about this one. So that's friction. So there's something similar to the friction, which is also you cannot avoid that, the resistive force or the drag force. So resistive force and drag force, well, it is the force when a body moving through a liquid or gas, the body experiences a drag force that opposes the relative motion and points in the direction in which the liquid flows relative to the body. So that means when, just like the drag force due to the air, when you are moving in the air, there will be a drag force in the opposite direction. So this force usually is proportional to the speed. The magnitude is proportional to the speed. Here, minus sign means in the opposite direction. This force is in the opposite direction, and the magnitude is proportional to the speed. But when you are moving with very large velocity, like the train or the airplane at a plane, the speed usually is very large. So that in that case, the force should be proportional to the v square. But for a car, what we all someone like us is walking in the air, it's usually proportional to the speed, the first order. So, okay, let's check this. A falling body in the air. So, actually, this is a model of someone as jump from the plane with parachute. So just like one with parachute here. So the force of gravity and the force Fd is the air drag force. So just like the one with parachute. So a free falling body in the air. In this case, there are two forces, mg and Fd, the air drag. So usually the force is proportional to Vf is equal to Bv. So minus Bv. So the net force is mg minus Bv and is equal to ma according to the Newton's second law. Okay, so and according to this equation, we know that originally, if the speed v, if v is small, v is small. So if v is small, mg minus bv should be positive, right? If v is small. So that means ma is positive and a in this direction. So that means it will this force will accelerate this object. This one will falling and will faster and faster, right? So this one will falling faster and faster. But when you are falling faster and faster, v is increasing. When v is increasing, maybe it at an instance, it will reach the value when v is equal to like mg over b. When v reach this value, this one will be equal to 0. If this one is equal to 0, which means a is equal to 0, it will no longer accelerate. It will no longer accelerate. That means it will keep its velocity. Okay, what's your question? Okay. Why is this, right? Because the drag force here, the force, drag force due to the L. The drag force due to the L, because just like, okay, if you are moving in the L, there will be a force due to the L, the drag force due to the L. And this force is proportional to your speed and in the opposite direction. Here, minus sign means in the opposite direction. Okay, is that clear? Okay, so let's go on. So two forces, one is in this direction, the gravity, and the other in the opposite direction, magnitude BV. So the net force is mg minus BV. The net force, F, like sigma, the total force. Okay, so when the speed is increasing and it reaches a terminal speed, which makes the acceleration to be 0, the speed will no longer increase. And in this situation, it will go on moving with this terminal speed Vt. So that's the case for people jump with the parachute. They jump from the airplane and accelerate. And after, if the height is enough, they will reach a state of uniform, moving with uniform speed in a straight line. So they are moving with uniform speed so that they can control how they land. So even you jump from the plane with a speed not equal to this, not start with from 0, still you will reach this speed. But the height is limited. You need to reach this speed as soon as possible. So before you land, right? So that's why when you jump from plane, originally at the very beginning, you will not use the parachute, right? You just falling and fast increasing and you can if you do not use the parachute, you can increase your speed very quickly. When you are close to this, and then you use your parachute, and you can reach the uniform speed very quickly. You can reach uniform speed very quick. So with limited height. So, but we can also prove this conclusion with calculus. So A is equal to dv over dt. So we need to calculate how long it takes to reach this terminal speed. How long it takes. And if the initial speed is 0, according to this, we separate the variables and integrate on both sides. We can reach this result. If you want to reach Vt, that means you need t approaches infinite. You need t approach infinite, which is not possible. But remember, here is okay. Here should be a minus sign here. There should be a minus sign here. But this one, it says it will approach infinite, so that it can approach Vt. But when t is large enough, the speed is almost Vt. Because this one, if you draw a diagram to show how it goes, it should be like this. So this period is very short, and after that is almost Vt. It's not exactly Vt, but almost. So, but if you feel that okay, this time is still too long, maybe I jump out of plane with not large enough height, with not large enough height. So you can do it like this. You can, just as I said, when you jump out of the plane, you may not use your parachute. And when you are close to this, and you can suddenly use your parachute, and then you can reach Vt much faster than start with 0. That means you are going to use the parachute when your speed are close to this, rather than start with 0. So, okay, so that's something about the terminal speed. So, the next part, steel dynamics, we are going to investigate the gravitation. The gravitation. So, gravitation is one part of the Newton's theory, and also very important because it determines how our universe works. Okay, so that's why the gravitational force is the one of the most important force in the universe. It determines how our universe works. So all the planets go around the sun because of the gravity between them. Okay, so first, before we start this chapter, there's a question. You don't need to tell me the answer. You can just guess and keep your answer in your mind. So, a space station revolves around the Earth as a satellite. So, 100 kilometers above the Earth's surface. What is the net force on an astronaut at rest inside this space station? You can say, okay, equal to her weight on the Earth, or a little less, or less than half, or zero, or somewhat larger than her weight. So you can guess and keep it in your mind. You don't need to tell me now. Just keep in your mind. Okay, in this chapter, we are going to investigate Newton's laws of universal gravitation and the gravitational field. Yes? What's your question? What's your question? Okay, you mean this is when you fall from some place very high. So when you from very high, okay, when you from very high, maybe, but if it's still a plane, not an aeroplane, if it's still a plane but not an aeroplane, you are still in the gravity of the Earth. We use the range of gravity of the Earth. You can still use this theory. These equations are still can be applied. But if you are if we are on a plane moving with a very large speed, or that can make you escape from the gravity of the Earth, that's different. But if there's no horizontal direction, just consider the vertical direction or the horizontal the speed in horizontal direction is just like the speed of a plane. That's not that you can also use all these equations. If the speed is large enough for you to escape from the Earth, that's different. If you have not escaped from the Earth, all these equations are almost the same, even from very high. Okay. For example, a helicopter, you can just use all this. If you start with speed 0, this one, just this one. Okay, that's a good question. Okay, so let's go on. So before Newton, Kepler has generalized several laws about the motion of planets. Because at that time, Kepler has a lot of data, has had a lot of data from very famous, another very famous experimental scientist. And Kepler is good at calculation. So when he generalized these three laws according to the data, So the three laws. The first one, all planets move in elliptical orbits with the sun at one focus. So it's not a circular path. It's a elliptical path. It's an elliptical, and the sun at one center. And that also works for as the moon moving around the Earth. So the moon moves in elliptical path with the Earth at one focus. And the radius vector drawn from the sun and the planet sweeps out equal areas in equal time interval. What does this mean? Okay, like this. Like, for example, this is the sun and this is the Earth. For example, after 1 month, the Earth is here. The radius vector from here to here, this area is the vector drawn from the sun to a planet sweeps during a month. And then another month, the Earth is here. This area should be equal to this area. And after another month, it's here. So this area should be equal to this and also equal to this. So that's what this second one tells us. The third one, the square of the orbital period of any planet is proportional to the cube of the semi-major axis of elliptical orbit. That means far from the sun, the orbital period should be longer. If you are far from the sun, So that's why the period of Pluto is much greater than the period of the Earth. So that's the Kepler's law. The Kepler's law, three laws. And Newton built his laws based on the Kepler's laws, but he has his own theory. The most important theory here is Newton realized that this gravitation is universal. So we all heard of the story, the apple hit Newton's head. So when the apple hit his head, he started to think, why does the falling object accelerate? So now we know it's because of the gravity, but at that time, people didn't realize this. At that time, people thought, if you want to apply a force on this object, you need to touch this object. Therefore, the force requires contact. So you need to contact this object so that you can apply a force on it. At that time, people believed that. So people do not know what apply force on the falling apple because nothing touched this apple. And people also do not know what the force make the moon go around the Earth. So now we know it's the gravity. So, but still, after we know the word gravity, still we do not know what exert the force of gravity. We do not know because there's no contact, and also what makes the moon move around the Earth. But Newton was a genius, so he realized that the Earth exerts a force on falling object and the moon, even though there is no contact and the two objects may be far away. No matter how far away, there will be a force between them. And the force is the same as the force between the Earth and the moon and Earth and the apple. And he tried to prove that, and he wanted to find out the quantity relationship of this gravitational force. Because first step, he tried to estimate the acceleration of the moon relative to Earth. Assume moon goes around the sun in a circular path. It's not a circular, but almost a circular. So if it is circular path, we know the distance from the center of the Earth to the moon, and we know the radius of the Earth, and we can calculate the acceleration of the moon. So because it's equal to v over r, v square over r, and here v, we know v. Okay, here. Sorry. So let's use a. Yeah. Here, according to the laws of circular motion, v is equal to 2 pi r, the length of the path over the period, right? That's the speed. The length of the path is 2 pi r, and the period is t, so that's the speed. We substitute it into here, we get this. And here r is this. And t, the period of the moon, is about 30 days. Just an estimation, that's enough. We only need to know the order of magnitude. So we use 30 days. So that we can get the result, the acceleration of the moon. Okay, we can compare it with the acceleration near the surface of the Earth. So, okay, this is the acceleration here. Then we want to find the acceleration here. So the acceleration here is about 9.8. The acceleration here. Sorry. Okay. The acceleration here is about g is equal to 9.8 meters per second square, while the acceleration here is this. Let's compare this. So we, according to this, we know about g a over g is almost equal to 1 over 3,600. By estimation, a rough estimation. Okay, if it's a rough estimation, let's compare these two. Okay, let's compare to these two. The radius of the Earth, and the radius of the moon orbit is the square root of this. That means the acceleration should be inversely proportional to the distance, square of the distance. So this is very important. The acceleration proportional to the square of the distance according to the Newton's second law. If the acceleration is proportional to the square of, inversely proportional to the square of distance, the force must be inversely proportional to this, right? And the force should be proportional to the mass according to the Newton's second law. So it should be proportional to the product of the mass, their masses, because according to the Newton's third law, if it is proportional to m1, it must be proportional to m2, because the force from m1 to m2 should be equal to the force from m2 to m1. So that's the Newton's law of universal gravitation. So universal means the force between any two particles. Every particle in the universe attracts every other particle. So that's why we call it universal. Not only the force between the planets, but also the force between any two objects. Every particle in the universe attracts every other particle with a force that is directly proportional to the product of the masses and inversely proportional to the square of the distance between them. So that's the universal law of Newton's law of universal gravitation. Okay, let's stop here today. Yeah, yes, good. Bye bye. So see you next week.